In this lecture, we are going to review Chapter 8, which is about rotational equilibrium and dynamics. Just like we did for translational motion, where we started with the kinematics, studying the motion regardless of the cause, then added dynamics, and the cause for translational motion is the force. We did the same for rotational motion. In Chapter 7, we learned the kinematics for rotational motion, and in this new chapter, we are going to learn about the dynamics. That is to say, we will take the cause of the rotational motion into the picture. Translational motion can be initiated by a force. On the other hand, rotational motion can be initiated by a torque. In this chapter, we are going to learn all about torque, what kind of factors it depends upon, and how it is related to the other variables of the rotational motion. As you can see in this first slide, you have a giant rock that is in an equilibrium status. We achieve equilibrium when the net external force is zero and the net external torque is zero, as we will learn in this chapter. We are ready to start learning about the rotational dynamics. We start learning first about a new physical quantity, which we call the torque, and we need this physical quantity, the torque, in order to understand how rotation occurs. We are all familiar with this situation. This is a door, and here you have the hinge of the door. The door can rotate around this hinge. You have the handle here. In order to open the door or close the door, we need to apply a force here at the handle. So the force that we apply here will allow us to open or close the door. The motion of the door is a rotational motion. All rotational motions occurs around some axis. So this motion occurs around the hinge here for the door. The effectiveness of this force that we apply depends on three important factors. The first factor is the magnitude of the force. The second factor is the position, whether we apply it here or half point here or nearer to the hinge. The location where we apply the force matters. And the third factor is the angle at which the force is applied. Maximum effect when the angle is 90 degrees here. We define the torque as the product of the force by the lever arm. This distance between the line of action of the force and the axis of rotation is called the lever arm. So the product of the force by the lever arm is equal to the torque. If the force was not perpendicular to the lever arm, then we need to apply trigonometry in order to determine the component of the force which is perpendicular to the lever arm. The unit for torque in the SI system is a unit of distance, R is measured in meter, multiplied by a unit of force, F is measured in Newton. So torque is measured in Newton meter. Consider this situation. We have this wrench and this bullet, and we are trying to loosen. So we apply a force on the wrench, and as a result of this force, there will be a torque. Due to the torque, there will be rotation, and the rotation will allow us to unscrew the bullet here. So as the force is applied further out along the wrench, the magnitude of the torque increases. So here we changed the point where we're applying the force. So this way we have greater torque compared to the first figure. Then here we are increasing the lever arm greater even compared to the second or first situations. So this situation will give us maximum torque, and will have the force, the same force, will have greatest effectiveness in this situation. So by just increasing the lever arm, we were able to achieve, by the same force, we were able to achieve the desired effect and loosen the bullet. Now, by convention, we consider the rotation counterclockwise to be positive, and the rotation that is clockwise to be negative. So here, the rotation due to this force will be counterclockwise. So the resulting torque is positive. If the force was applied in the other direction, this way, it will be clockwise, and that way the torque will be negative. Torque is a vector quantity. As you see here, we use the Greek letter tau for torque. It is a vector quantity, and it can be determined from the direction of R and F according to a right-hand rule. If you open your right hand and assign the direction of the four fingers to R, and then curl them toward F, then your thumb will determine the direction of the torque. Okay, so the four fingers have the direction of R, then the curling of the four fingers will be toward F, toward the direction of F. In that case, the thumb of the right hand is pointing up along the z-axis. That would be the direction of the torque. So now we understand that the only way to create rotational motion is to apply a torque, and the rate of rotation of an object does not change unless the object is acted on by a net external torque. Okay, so just like in a translation motion, the object will not change its velocity, its motion, except if we acted on the object by a net external force. The same story here for rotational motion. Rotation will not occur, the rotational acceleration will not change unless we have a net external torque acting. Example: the woman on the left exerts a force of 625 Newton perpendicular to the door and 1.2 meter from the hub's center. This lever arm is 1.2 meter. While the man on the right here exerts a force of 850 newtons. The force here is 850 newtons perpendicular to the door and 0.8 meter from the hub's center. So R2 here, the lever arm for the second force, is 0.8 meter. Find the net torque on the revolving door. We are interested in the net torque that is acting on the revolving door. Now, the net torque is the superposition of the two torques, due to F1 and F2. We check on the torque due to F1. F1 will create rotation clockwise around this hub. Therefore, the torque due to F1 is negative. So tau 1 is the torque due to force 1, is negative R1 F1. R1 is 1.2 meter, F1 is 625 in newtons. This is minus 750 in Newton meter. Then for the other force here, this creates rotation counterclockwise because it's going to rotate around the hub counterclockwise, as you can see the motion of the mouse on the screen here. Okay, this is counterclockwise. So the torque due to F2 is positive. So tau 2 is R2 F2 0.8 multiplied by 850. This is 680 in Newton meter, and it is positive. The net torque, we need to add tau 1 to tau 2. So when you add the numbers here, you get the difference between 750 and 680. It is 70 in Newton meter, and it is negative. So the net torque, the net rotation will be clockwise, will be going this way, and the net torque is 70 in Newton meter. So now we have a better understanding for rotational motion and for torque and how to calculate the torque due to any force or set of forces. In general, the line of action of the force may not be perpendicular, as was the case here, and in these situations, the force was perpendicular to the lever arm. So if the force is not perpendicular to the lever arm, like these situations, then we are interested in the perpendicular component of the force, and we determine the perpendicular component of the force simply by using trigonometry. The perpendicular component is F sine theta. If the angle between the force and the lever arm is theta, then the perpendicular component here is F sine theta, and the parallel component is F cosine theta. We are not interested in the parallel component. We are interested in the perpendicular component when we calculate the torque. So the perpendicular component is F sine theta. So for this situation, theta is 0. Therefore, F sine theta is 0. Same, if theta is 180 degrees, sine 180 is also 0. So F sine theta is 0. The torque due to such a force will be 0. If it is 90 degrees or 270 degrees, then sine of 90 or sine of 270, you are talking 1, and that is the maximum possible value for the torque. In general, torque equals Rf sine theta. So we have these three factors now to deal with: the lever arm R, the force F, and the angle between F and R. We are interested in that angle. So here, if we consider the wrench and the bullet again here, now we are allowing the force to change its direction, not position. It's the same position, this drawing and that drawing, but the angle is being changed. We will note that the torque changes as the angle gets bigger and bigger, because sine, the angle will increase as the angle increases, until it becomes 90 degrees. At that point, we have maximum torque. Okay, so now we understand this game, we understand the force, we understand the lever arm. We are in a position to calculate the torque for various situations. And as I said, torque is a vector quantity. It has both magnitude and direction. This is just a reminder about the right-hand rule that we will use to determine the direction of the torque. So here you point the fingers of your right hand on the direction of R and curl the four fingers toward the direction of the force vector V. Then the thumb of your right hand will point in the direction of the torque, which is going to be going out of the screen, perpendicular to the screen and going outward. Sine of theta here is equal to sine of theta here. So whether it is 60 degrees or 120 degrees, it is the same value for sine. Whether it is 30 degrees or 150 degrees, it is the same value for sine theta.